So our next speaker is Tobias Kümmerle. He's Associate Professor for Biogeography and Conservation Biology at the Geography Department of the Humboldt-Universität Berlin here in Germany. And his research focuses on the understanding of human and environmental systems on the land. And his presentation is entitled Observing Land Cover Change and Land System Transitions. Thank you.
Thank you, Mercedes. And thank you all for coming here today. And thanks to the Scientific Steering Committee of this conference for giving me the opportunity to give a keynote here. It's certainly something I didn't expect 4 years ago when I was in Arizona on the first GLP OSM. So exciting. I'm dealing with a pretty broad title here. And I want to use that title to give you an overview on my personal flavor on where we stand in terms of observing land system change at the moment. I want to highlight a couple of exciting developments, and I think there are really a number of them, and also some challenges that we are still facing in that regard. So let's see if this is working. I wanted to start with this image, a satellite image, Landsat ETM Plus image from an area in Kansas. And I think such images are fascinating. I have been fascinated by them for a long time. What you can see here are irrigation agricultural plots at various phenology stages. But looking at these images, you start asking questions like, what is it that we see here? Who or which drivers led to these patterns appear in landscapes? How did these areas look like before humans started to transform them very radically? And what do these transformations mean for ecosystems, for biodiversity, for certain things we expect in landscapes? Now, these are fundamental themes in land change science, and for each of these questions, we have many, many sessions here in this conference. So observing land and observing changes in land use are often the starting point for us to ask questions that are fundamental to land change science. So now, that is certainly not a new thing. And a lot of people have used observations of landscapes as a starting point to ask more deeper questions about how people and the environment interrelate. And I could have chosen a much earlier example here, but I thought being at Humboldt-University, Alexander von Humboldt should make at least one appearance at this conference. And so here he is in front of the Chimborazo in Ecuador that he's about to climb. And I'm sure many of you are familiar with his works. When climbing this mountain in various expeditions, he was documenting, observing and then documenting in very great detail how climate interacts or affects vegetation along the elevation gradients, but also how land use changes along the elevation gradient and how people affect vegetation patterns. Now, while Humboldt was really focusing on the natural world and on vegetation, Karl Ritter, Germany's first geography professor, also at this institute, was really more interested in the interactions of people and nature. And also for him, observations of landscapes and how people were transforming landscapes in the 18th and 19th century were a big starting point or a big motivation to think more about what these interactions really mean, and come up with his work, the relationship of nature and geography. Now, since the days of Alexander von Humboldt and Karl Ritter, we have certainly come a long way. And we can now basically take our mobile phones almost anywhere on this planet and zoom into almost any place on the planet and observe landscapes there. And we can do that for even the most remotest places, such as the place that I'm showing here. That's the north of Argentina. Someone has just mentioned the north of Argentina. That is the Chaco region, a region where I've started to work recently. And this region was formerly called the Impenetrable. Very hard to travel in these environments. Very remote place, but recently this region has come into focus for agricultural expansion. What we see here is the expansion of soybean production especially, but also cattle ranching, making this region into one of the global deforestation hotspots. Now, we cannot just zoom into this region and see what's going on there in very great detail using tools like Google Earth, but we can also go back to the satellite record that we have now for about 30 years or so, and try to understand how this process, in this case the deforestation process, worked. And I'm not sure if this video is going to start now. So what you could see on this video, if it would run as it just did half an hour ago, All right, what you could see on this webpage, also a Google product here, time-lapse, that makes use of the Landsat satellite archive, is how for yearly time slots, in this case, this deforestation pattern unfolds in that case. So go to the webpage and see the video. It's not that spectacular. I'm just showing it as an example of how you can really see the evolution of land change and the transformation of landscapes in really great detail for anywhere on the globe now. It's the time-lapse here. So how far have we come in terms of observing land systems at broad scales? And I want to approach this question in 3 parts. We're through the introduction here, and I want to focus now a little bit on observing land cover change, so mainly talking about satellite remote sensing. And we'll then want to talk about land use intensity changes and land management changes that would fit really nicely to what Earl has talked about before me. And then in the last part of this talk, I want to try to tackle the most challenging aspect of the title that Peter has asked me to talk about, how we can observe land system change or land system transitions. So let's start with the land cover part. So arguably, we now are in a situation where we have the most detailed picture of the globe ever. There are more land-focused satellite sensors in space than ever, streaming a really wide variety of imagery of different spatial, spectral, and temporal resolutions. And perhaps equally importantly, there are processing systems in place that use these imagery and provide us with secondary products that are a lot easier to work with for many of the land change science community that are not really deeply into the remote sensing aspects of it. And here you can see one such product that's a fine-scale, relatively fine-scale land cover map, the glob cover product from the MARIS satellites at a resolution of 300 meters. Products like that, it's just breathtaking when you go back to what the situation was like 10 years ago, 20 years ago, and how far we have come in regards to really mapping land cover and land use at broad scales. Nevertheless, there are still quite big limitations and gaps here. Most global products that we have are still relatively coarse in scale, relatively coarse relative to the processes that we're usually interested in, the land change processes that we are interested in. Most products still represent snapshots in time. Or if we have time series, they are quite short, 10 years, maybe 20 years. There's a big and continued need for homogenization of legends. It's not straightforward to compare different land cover products to each other. And there's a lack of systematically sampled calibration and validation data, simply because it's so costly to really generate these data, large amounts of calibration and validation data that we would need to parameterize and compare different global land cover products. And due to these reasons and others, we see quite substantial differences in the global land cover maps that we have at this point. Now, this is an image from the GeoWiki webpage that you may know. That's work that Steffen Fritz and others at IASA have been setting up. A part of this webpage compares global land cover products. In this case, the GLC 2000, the MODIS land cover map, and the glob cover map. And the different colors that you can see here point to disagreement between these maps. And the yellow colors that you can see here, the more yellow or the more dark the yellow is, the more disagreement between these 3 maps we have in terms of cropland in an area that we know in terms of cropland expansion and intensification has been quite dynamic, in this case Latin America, with a focus on Brazil here. So the problem now is that we cannot simply take one of these maps, because one map may be better in one place, but in another place another map is better. Plus, we cannot easily say which map is actually better if we lack ground data to make that call. So it's not straightforward to choose a map here. Now, before the Global Land Project Open Science meeting, we had a 2-day workshop bringing together remote sensors focusing on land use and land cover change, both from the NASA community and from the European community. And I just wanted to sort of summarize some of the opportunities and some of the things that were discussed there. And in one sentence, summarizing it in one sentence here, is that there was really this mood of enthusiasm in these 2 days, that we may now be in really truly exciting times to be involved in remote sensing for land change science. I'm not really sure I can convey this enthusiasm well. I put it in red here, but it doesn't really it doesn't really help that much. Yeah, but I think every one of the keynote speakers made that point that it's truly exciting times in terms of satellite remote sensing for land change science applications, and I try to summarize the reasons for that. So the first reason is that we have new sensors available. Now, there have been, for sure, at every conference over the last 20, 30 years, remote sensors speaking about the new opportunities connected to new sensors. But now this is a different situation because we now have sensors that gather data that are really useful for land change science application because they are at moderate resolution, so 10 to, let's say, 50, 70 meters. And we do not just have new sensors, but we have several of them. With Landsat 8 successfully launched about a year ago, and with the Sentinels, especially Sentinel-2, scheduled to launch next year, the first one and then another one, we're talking about sensor constellations. So several of these sensors that will have a relatively high repeat rate, and they collect a lot more images than in the past, allowing us to really get a more detailed picture of what's going on the ground and better understand things like agricultural change or dynamics in agricultural lands. Equally important, there are new technologies to make use of those opportunities. That's, on the one hand, advances on the processing side. Relatively automatically, these images are now transformed to a format that we can actually work with them easier. We also are in a time where processing power doesn't seem to be the issue anymore. We can do things with cloud computing that we just would not have imagined 10 years ago that are possible now. But perhaps the biggest change that we are experiencing now are fundamental paradigm shifts in data policy and access. And that is, on the one hand, the case for new satellites that are put up, where data are usually now entering the public domain, and there's access to these data sets, but also the data that has been collected over the last 30 years, 40 years or so, for example, in the case of the Landsat program, are increasingly made available to researchers. And that is something that is really a game changer in remote sensing, a huge change in how we think about analyzing imagery. And many of the people who have pushed for that are actually here at the conference, Tom Lovell and Curtis Woodcock leading the Landsat team, Gilberto Camara. So thanks to them, we really now have access to the Landsat archives and can move away from handling individual images towards using all available data. And that will help us to resolve a little bit better the heterogeneity that we have in land systems, in broad land use classes such as croplands. Here, 6 examples of different cropland-dominated landscapes across the globe that we are currently lumping together, if we're lucky, in one class in those global maps. I'd like to show a couple of examples of how using the entire Landsat archive can make a difference to really understand better what's going on the ground. This first example is the work of Hannes Müller, one of our PhD students. He focuses on deforestation in the Amazon. Here you can see just 2 individual plots. The green line is from a mature forest plot where nothing has happened over this 30-year time period. And the red line is from a plot that has been deforested for pasture. Now, the individual dots that you can see here are individual Landsat observations, one particular spectral measure here, Tesla cap wetness. And you can see a couple of interesting things. On the one hand, you can see that deforestation was not necessarily a drastic conversion of this forest canopy. It was more a gradual process because what you have there is a relatively extensive pasture that still has quite a high ratio of tree cover, and then trees are removed gradually over this 20-year time period. So this gradual process we would have a really hard time to capturing would we analyze 2 images as we have done a lot in the past. And the second thing that you can see here is that if you would have picked an image from the 1990s and then you would have picked another image from, let's say, the 2010s, it would have been quite hard to pick the right image, or depending on which image you would pick, you would get a quite different picture, and sometimes it would be very hard to detect that there have been changes at all. So by using all available data, by using the time series, we can get a much better understanding of this gradual change process that we see there. Now, this is work by Patrick Griffiths, also from our team here, who has looked at Eastern Europe region, a mountain region here, the Carpathian Mountains, Romania, Poland, Slovakia, Czech Republic. And his interest really was to reconstruct land use change. Since 1985, the breakdown of the Soviet Union has led to dramatic land use changes in that area. What you can see here now in different colors are, you can see the frames of individual landsat footprints. And the more yellow the color is, the more observations we have in this particular location for a particular focus year, in this case 2000. Now, sometimes these are hundreds of observations, and then we can choose for every particular spot in that area that interests us the observation that fits best our interests. So, for example, we would like a summer observation, and we can transform from all these observations. We can generate what's called a composite image, a sort of mosaic image, where we pick the best observation for each location and generate what you can see here, these composites. Now, these composites are cloud-free, homogeneous. They are a lot easier to work with and to translate when you do this for multiple times into land change maps such as this one, where you can see different land change processes in yellow, for example, agricultural abandonment or extensification that is especially widespread in Ukraine and Romania here. Now, the first attempts to do that at the global scale, truly fascinating results are at the moment becoming available here. This is work from the Wealth Project that is led by David Roy, who's also here at the conference. And he has been doing a similar task, but for the globe, handling about 120,000 Landsat images to produce this composite image, global composite image for around the year 2010. And these images will become available for download soon. Now, using the entire Landsat archive, you can also start mapping changes in land cover that have happened over the last 10, 20, 30 years. The archives extend back to the early 80s or even 70s. And this is work that I'm sure you're familiar with and have seen the very prominently published paper by Matt Hansen, who have been reconstructing forest cover changes for the period 2010 to 2012. This is the most fine-scale, 30-meter resolution forest change map that we have right now. And zooming into this map, I'm now going to zoom in again in this region in northern Argentina, the Chaco region. You can see the level of detail: red, deforestation areas, green, forest areas, black areas that have been deforested before 2000. And just the level of detail, I think, is amazing that we can get out of these maps. But it's not just that we're getting a deforestation map. Because we have the entire archive, we can also say a lot more when this deforestation happened. So we get a lot more detailed data out of this. Now, you have to keep in mind that this is the first analysis of this kind that has been done. So we're really only at the beginning of using the entire Landsat archive for land change applications, but it's truly exciting results that we're already getting. So expect a lot of interesting things to happen in this arena. So summarizing this part, we really see paradigm shifts in Earth observation for land change science. Rapid increase in data availability and in data access. And that allows us to analyze all available data. Now, I've talked about the Landsat archive, but there is also interesting work in integrating the Landsat archive with other types of sensors to do multi-sensor applications, multi-scale applications. And summarizing this in the words of Curtis Woodcock, this will allow us to detect more subtle kinds of land change, detect change more reliably than we have been doing in the past, reconstruct comprehensive land change histories, at least back to the 70s, and detect land change as it is occurring. But we're only at the beginning. So now, moving on to land management change and moving on a little bit quicker, as Mercedes has told me. Now, we've still been talking about land cover only, but we're mainly interested in land use in the context of this community. So translating land cover to land use remains a challenge. Now, I'm showing you one example of how this can become a little bit easier when we have time series data. This is work by Stefan Estel, who is interested in mapping fallow and active agriculture, whether agricultural land is used or not, across Europe. And Europe here defined as ending at the Urals. In blue, you see active farmland. In orange, you see fallow farmland for the year 2005. And you can see that in Eastern Europe, there are a lot of agricultural areas that are not used. This is a legacy of the breakdown of the Soviet Union. Now, because we have, in this case, that work was done using MODIS data, because we have MODIS data for a 12-year period, we can produce such maps for every year of the MODIS record, and then we can overlay them and get maps like that that shows the fallow frequency, how often a particular plot is used. Now, that is already a direct indicator of land use intensity, very closely related to what we have heard before, and it gives us a much more nuanced picture of what's really going on. For example, again, looking at Eastern Europe, we can see that some areas are actually almost never used or not used, whereas other areas just have long fallow cycles. So they're not actually abandoned, but they're just used at a relatively low intensity every 5 years or so. Now, these are still land cover information, but we can now define on top of this time series, particular land use processes such as what would we consider abandonment, what would we consider recultivation of land that is not used. And I'm just showing you one example here. This is a map of recultivation of abandoned land, of land that is not used in the first half of the MODIS record, but then starts to be getting used again in the second half of the MODIS record. And you can see pockets of recultivation, especially in European Russia, but also in Romania, that has joined the EU in 2007, and in other places in Eastern Europe. Still, we can go only that far looking at land cover when thinking about intensity. And I wanted to highlight this with this picture here. What you see here is in this orange, the orange line shows you cropland area in the EU and how it has changed relative to 1960 over the last 50 years or so. Basically, it hasn't changed a lot, and you can see a stable situation. But at the same time, we see massive increases in production. So yields have increased a lot, doubled, more than doubled. So obviously, there is a big intensification process going on that we will not really be able to capture with remote sensing data alone. Now, Annette has already highlighted this initiative that we had in the Global Land Project to think about how we can capture land use intensity and perhaps frame land use intensity. I'm going to focus today here on the mapping part regarding land use intensity. And you can see this framework that was shown yesterday, that we think of a production system as things going in, inputs, things going out, outputs, production. But also this production system being a coupled human-natural system with properties both on the natural and societal side of things. Now, when mapping land use intensity, you want to put things into relation here. You can do that either on the input side, how much fertilizer is used per land unit. You can put into relation inputs and outputs, that we do when we calculate yields, for example. Or you can put into relation either inputs or outputs with system properties. That would be yield gaps or the share of human appropriated NPP. So for mapping many of these metrics, of these land use intensity metrics, what you need to do is to combine ground data with satellite data or with satellite products. And often that means that the ground data is not really available at the level where it was collected on the ground, but in aggregate form. And so we are dealing with statistical tools to really link those data. So we're not anymore really strictly dealing with observations, just to keep that in mind. There have been tremendous advances in mapping land use intensity over the last decade or so, especially the work by John Foley's group, Naveen Ramankati, Stefan Siebert. We've really come a long way here, but nevertheless, the situation regarding really understanding broad-scale patterns of land use intensity is problematic. Now, this is a bit my subjective summary of a bigger table that you will find in the reference down here in this traffic light system, showing that in terms of extent of huge or broad land use classes like croplands, grazing land, and forests. We have data available. For cropland, the situation is pretty good in terms of different types of intensity metrics. But keep in mind, they're all dependent on the land cover maps. So all the uncertainty in the land cover maps will be somehow reflected in these intensity metrics as well. But there are big data gaps, especially for grazing land and also for forestry, where we really do not have a lot of fine-scale information available. So summary around that part, there's still a lot of room for improvement regarding data sets on land management. And the advances on the remote sensing side that I have been talking about will really make a difference here, hopefully, as well in the next coming years. But the biggest challenge and the biggest lag we are facing here is ground data on land management. homogenizing and standardizing data, and especially data access here as well. There are a lot of interesting initiatives at the moment. There are a couple of sessions here focusing on that. Achieving better data sharing for ground data on land management. You may have seen the GeoShare session yesterday. There are crowdsourcing tools that seem to be very promising to gather data for data sparse regions. Again, GeoWiki is something to mention here. And there are also standardization, harmonization, and validation efforts in that arena, similar to the land cover arena. So the last part and shortest part of my talk is gonna focus on land system change, and just wanted to say that using these new data sets that have become available over the last 10 years or so, we have also started to map land systems. Now, this is work that Peter Verburg has done, Earl Ellis and Naveen Ramankadi have done work on the landforms that you are, I'm sure, familiar with. We've seen them before, that in a way also belong into this field here. This is another approach, that a more data-driven, more bottom-up approach done by Thomas Watzlawick, who's sitting here. So we're making advances here, but we're still dependent on the input data here. And the problems in the input data will not really allow us to track these changes back in time for a while. And I also wanted to highlight that really to get at the transitions in land systems, we often need much longer time series than what we get from the satellite record. So in this case, again, the Carpathians, where Catalina Munteanu has spent a lot of time and worked together with many, many collaborators in the individual countries to make available and digitize old topographic maps that include land use. Now, this was the 1860s, and we have a lot of time layers in between, but I just show that in contrast to 2005, and you can see the big transition that has been going on, a forest transition in this case, and to capture that, to observe that, to map it, we need the old maps. And as a last example, I just wanted to go back to this issue of the stable croplands in Europe. In this pinkish colors, you can see all areas that haven't changed in terms of cropland extent, but then when you look at the trade-related land use footprints that Europe has been creating, so that links back to the teleconnections issues that we have heard a lot about yesterday already from Annette and others, and Eric. You can see now how, this is a picture from 1987, work by Thomas Kastner and others, and now 2008. We can see that the land use footprint of the EU has increased substantially over this time period, and also that the topology of this network has changed quite a lot. So even if we are observing landscapes as stable, the land system may be changing quite rapidly. So we have to combine our place-based research with network type of research, and how to do that in a quantitative way remains a challenge. So I think I'm getting a lot of signals here that I've run over time, so I'm just stopping here. These are the points that I've already made. Thank you for listening.